So good morning, everyone, once more. I'm Sudeshna, and I'm going to be with you for this virtual series talk on water sustainability and water management. And before I start sharing my screen and begin the talk, I would like to just point out that this session is being recorded. The recording is going to be available via the virtual series website. So I hope that you all are okay with that. Regarding questions and answers, I'll be very happy to answer your questions at the end of the presentation. So during the talk, if anything comes to your mind, do put it on the Q&A and I'll have a look at the end. And also to mention that at the end, you will have a feedback form to fill up at some point of time. I don't know if it's right at the end of the presentation, but it'll be very helpful if you do that because we always work on your feedback. So with that, I'll start sharing my screen with you for the presentation. If you give me a minute, please. And yeah, do the slideshow. So I hope you can all see my screen. So thank you all for joining us today for this virtual lecture series on Spring into STEM. And the talk today is on interdisciplinary and sustainable water management. And I'm Sudeshna. So first of all, I would just like to introduce myself. You might have already seen it through the link on the virtual lecture series website, but just in case, I am a lecturer teaching in chemical engineering. My teaching focuses on geology for global managers and engineers. So it's a very interdisciplinary approach to my teaching. I also coordinate the module, the integrated hydrogeology and sustainable water management. Much of the content of today's talk is taken from that module. So it gives an idea what that module actually covers. And I supervise dissertation and I'm responsible for teaching students on how to improve and develop their research skills. As always, for mostly everyone in UCL, our teaching is very much interrelated with our research. My research interests lie on natural resources. It's a wide range that I am interested in, right from carbonatites, which are very rare earth element rocks, deep sea sediments, the gas shells, and a very important natural resource, that's water, of which I'm going to talk to you about today. Energy transition is also one of my top research interests because I think it's very important as we make our journey, as we make decisions on how we move from today's world dominated by fossil fuels to renewables for tomorrow. So in between, the energy mix is something I like to focus on. When it comes to water, I like to look at it from the perspective of circular economy as against linear economy. Circular economy when the management of these resources are more environment friendly. So on that, the wastewater management is very critical. We'll have a look at it very briefly in the presentation today. And finally, I'm interested in educational aspects, which makes my teaching more inclusive and incorporates different techniques that's beneficial for my students. So why is this so important, talking about water management and natural resources? It is one of the sustainable development goals, one of the 17 sustainable development goals of UN. And it is accepted by all member nations that water is fundamental, very fundamental to the prosperity of every country. Water, the usage of water should be almost like a fundamental right, and it should not be competitive. It should be more based on cooperation between the countries. And So there is something that's very important about it. There is an existential challenge to make sure that this fresh water for drinking, fresh water that's needed for the economic growth of the countries is available. And it's like a moral obligation. UCL is committed to helping to support all the UN's Sustainable Development Goals, including clean water and sanitation. And they do that through its world-class research and teaching and external engagement. And that's where we come in as well. That's where I come in as well. So as a lecturer teaching, I'm connected with the MSc Global Management of Natural Resources program. So the module on hydrogeology that I teach and the content of today's talk is based, as I said, it takes aspects from that module. It's part of this program, the MSc Global Management of Natural Resources. If you want to know a bit more about the program, please visit the website through the department. Please use the link. The link is given below to the departmental website. And the program is interdisciplinary in nature. And the program is also transcontinental between London and South Australia. So what is essentially going to be covered in the module, Integrated Hydrogeology and Sustainable Water Management? Now, if we look at water management, we need to understand about the groundwater, the subsurface water flow, and how it connects to the surface water bodies and the surface water flow. This is a fundamental basis of understanding water management. And then we need to be very focused on understanding when it comes to the groundwater, because as you will realize, that is the biggest storage source for our fresh water. We need to understand about the groundwater abstraction and versus groundwater recharge. So this is an important aspect the module is going to begin with. And then we're going to look at water usage in different sectors, domestic, the mining, the hydrocarbons, and how can we treat the water so that it can be reused better. And that will look into technologies, that will look into the social impacts, the social policies, and the role of the different stakeholders. And finally, the students should be able to link it all together to get a complete picture. If you want to know more about this module, again, you can use the link from our department and the program website. So again, we would be using a lot of case studies in the module. For example, in London, we are in the brink of water crisis. There is already some water stress, which is going to be augmented in future. We're going to see acceleration of that in the future. There are a number of reasons for it. One is obviously the rising demand due to population growth and the change in the lifestyle. And then we also have to take into picture the forecasting, looking forward and doing some modeling as to how is the population going to grow in the future, as well as how is this natural resource that's available to us going to change in the future. So that is very important in order to plan our water management. So as I said, UCL is committed. So when it comes to water management, we have started in UCL, and that's a wonderful case study to look at, improving water efficiencies in UCL buildings. We have about 250 to 300 buildings. So when you look around, it's a wonderful case study to see how water management can be improved on, what is being done well and what is not being done well, where there is scope for doing better. And for that, what we use is the BREEAM's new construction. BREEAM's is a way of assessing sustainability for buildings. It could be new buildings, it could be buildings that is already in use or that's undergoing refurbishment. And so this is about assessing how well we are doing in terms of environment from the perspective of meeting environmental requirements. When it comes to water, what it looks at is the water consumption, water monitoring, water leak detection, and water efficient equipment. And there are ways how credits can be accorded for each of them. So this is an initiative that UCL takes very seriously, and wherever there is scope, as says Ben Stubbs from the Sustainable UCL, we try to implement it and raise our credit points. So what are we doing? It starts from very small things like specify efficient sanitary fittings. For example, at the new UCL Student Center, which is a wonderful facility for students that's newly available. So they have the low flush toilets, they have water efficient shower facilities. We are trying to monitor the ongoing water usage as best as we can. So besides the central water meter, there are sub-meters that look into the water consumption for individual plants, individual buildings, where the water consumption is more than 10%. The other things that is being considered is rainwater harvesting, wastewater recycling, putting down the right roofs so that the water can be utilized better. So there are little things that hopefully will go a big way. It all starts, so that was UCL, but on a global scale, it all starts with the hydrologic cycle. I think most of you are familiar with the hydrologic cycle and the processes governing the hydrological cycle. For example, the evaporation, condensation, transpiration, evapotranspiration, and precipitation. Where do we begin in the hydrological cycle? It's a cycle, so there is no beginning, there is no end. One thing to bear in mind is that the fresh water is only 2% of the total water, of which 98% is in groundwater. So that is something when people look into the hydrologic cycle that just should be kept in mind. Whereas when you compare it with the water being held in the vapor state, it's just 0.001%. So it is not evenly distributed, of course. But when it comes to the starting point, so let's start with the oceans, because ocean is the largest source. So when you look at the oceans and when you look at how the water is cycled, the process that happens there is evaporation. And from evaporation, it leads on to precipitation. After precipitation, the water can be locked up in the ice and snow. It can precipitate on land, and you can have the surface flow of water. On the other hand, a fraction of it may infiltrate. Besides, you can have the water that is trapped or held in the different water bodies on the surface. So when the water infiltrates into the ground, you have the water in the soil layer, where the pore spaces of the soil has water and air. But if you go deeper down, there is that layer of rocks where the water saturates all the pore spaces. By the pore spaces, I mean the voids that are present. That is where the groundwater comes in. The water is in the soil layer is again available through plants, plant roots, and then through transpiration, part of it goes back into the atmosphere. And underground water, some of it can go and supply some water to other water bodies, and some of them will be stored there, and we can access it if we need to, but access it smartly, of course. And there is another small component of the hydrologic cycle. Nevertheless, it should not be missed. That's the magmatic water. The magmatic water is stored deep into the earth, and it sometimes comes up during volcanic eruptions, and it has an impact on the hydrological cycle. So as I said, fresh water is something that directly impacts us. So when we are talking about accessibility of water to the human population, we're talking about water security. Generally, we refer to fresh water. So the fresh water storage is very important. It can be stored in many forms, in many reservoirs, in the ponds and tanks, aquifers, soil moisture, natural wetlands. What would be important to consider is the storage reliability and how it can be accessed in an environment-friendly way, the cost implications, and the management complexity. So when you look at the freshwater storage, these are the aspects that people working on water management will be concerned about. We need to keep in mind how we can access this freshwater storage. For example, the soil moisture is generally accessible through planting crops, whereas the aquifer, the shallow or the deep, you need to think about the wells and the boreholes. So how does it impact the environment? What is the cost that is associated with it? And then, as I mentioned, the storage reliability. For example, the deep aquifers are expected to be generally less perturbed than the shallow aquifers. So it is more reliable in terms of storage, unless and until we, human intervention changes this balance or affects this balance. So 98% of this fresh water is locked in the aquifer after infiltration through the soil layer. So when we look at the aquifer, we would be concerned about, we would like to look at the type of aquifer. On one end, we have this aquifer with enough porosity. Porosity is the void spaces and sufficient permeability. When I say permeability, it is the interconnection of these pores. So it works like a pipeline. If the pores are like a storage unit, when they are interconnected, they serve serve the purpose of a pipeline and helps in water transmission. So aquifer, that is that which can store and transmit water, like sand and gravel, sandstone, different types of rocks. Even the same type of rock needs to be assessed very carefully for the porosity, permeability, and other attributes. So that's where understanding of water as a natural resource becomes important. On the other hand, you can have aquifuge. It has no interconnected openings, neither does it have enough interstices or spaces. So it cannot transmit water or store water. In between, you have the aquiclude. The aquiclude transmits water. It definitely stores water. It transmits water, but at a lower rate. It's not it cannot supply enough for a well or spring. And then you have the aquifer, that's just like a storage unit completely. It does not allow the flow of water at all. So when we look at this, the underground water storage, we need to take into account the kind of storage we are talking about. So the water management, the main challenge that's facing the water managers is the freshwater stress that I've mentioned. That is why there is so much of emphasis of understanding the aquifer. And there is so much of emphasis on understanding the hydrologic cycle, because the underground water is all connected to the entire cycle. So the freshwater stress, it depends on population growth. It also depends on how we are consuming the water, whether we are wasting water, we are being able to recycle water. All these aspects come into question. But what is not included here, but it's important and equally critical, is the climate change and how it's going to affect the availability of water resources. So that also needs to be taken into account by people working on water management. So fresh water is important. It's essential for everything. It's essential for health. It's important for economy. So it is embedded in all forms of development. So when we are talking about a sustainability development goal on water accessibility, it is connected to climate action. It's connected to food security. It's also connected to the development goal on economy. So that is why it is so very important. So as the American President John F. Kennedy had said, anyone who can solve the problems of water will be worthy of 2 Nobel Prizes, one for peace and one for science. And this was said many years back, but it holds good even now. Water management is also very is important, it's critical, as well as it's very challenging, because how do you value water? That's one important thing that comes to play, that comes into discussion, but the answer is never straightforward. Valuation of water needs to be need to be taken into in various from various domains. For example, obviously, the water resources that are available, the ecosystem, the water ecosystem is the first consideration. But equally important is the water infrastructure. How are we storing water? How are we going to reuse water? That's going to play a major role in water security. The water services, for example, water treatment, drinking water, sanitation, related human health aspects, and then the industrial development of country. How is it managing the water consumption for agriculture, for industry, for energy resources? All these together play a role. And add to that the socio-cultural attributes, which is related to recreational, cultural, and spiritual activities. So everything needs to be considered together. That makes it so challenging and interesting as well. So as I said, important to the water management is looking at the reuse of water, recycling of water. So we are now focused on looking at it from a circular economy perspective rather than a linear economic perspective. The linear economic perspective for any natural resource, for any good, would be make, use, and throw. When it comes to the circular economy, what we would like to do is increase the longevity of the product, whatever resource we are talking of. Here it's water. Get the maximum benefit out of it when that's in use, and finally recover and regenerate the products the best as we can. And for water, the wastewater treatment comes into play there. So when it comes to the wastewater treatment, we obviously have to characterize the wastewater. So here are some attributes that are used to characterize the wastewater. For example, the solids that are present, the volatiles that are dissolved, the temperature, the odor, and the chemical attributes like the organic content, the oxygen demand, both biochemical oxygen demand and chemical oxygen demand. They are an indication of the pollutants that are present in the water. You consider the alkalinity, the pH, and the other attributes like the chloride, sulfur, heavy metals, and carbohydrates, nitrogen and phosphorus. These two are very important, and they're often commonly used to characterize wastewater. Then there are other biological attributes, including the viral loading, and of course, any animals and plants, etc., that's present in the water that we are considering. In this context, like when you're talking about wastewater, the wastewater treatment is important. Wastewater is studied for various other reasons. I don't know if you have seen this news item. This is a very important, it was an important science paper, a high impact science paper in Nature in 2020, when scientists actually measured the sewage water and they could find traces of the coronavirus in that sewage water in at least 3 countries like US, Sweden, Netherlands. What does it mean? It means we are being able to survey a population of over 1 million this way. There are complexities associated with it, remember, because we need to know the load of the RNA in the fecal matter if we are going to use this to trace back how the virus is spreading. That's one thing that would be very, very important to be able to do. And obviously selection of a representative population, but it also highlights how wastewater can be important. Yes, wastewater can be treated and put back into the system for use, but wastewater can be used for other kinds of studies as well. When we are talking about wastewater and how groundwater is contaminated, not suitable for use anymore, arsenic contamination, it happens in various parts of the world, but the Bengal basin is very, very famous for it. You might be aware of it. We would expect the arsenic concentration acceptable level to be less than 10 micrograms per liter, but it's way higher than that in many regions of the Bengal basin. So there was a leading study by a UCL team of researchers, Professor Burgess et al., who looked into arsenic contamination of groundwater in this region, looking into water samples in a number of hundreds of wells and studying them for arsenic and looking at how, what is a situation that allows the arsenic to reach our deep groundwater resources, and what is it that can stop them from reaching there. And they were looking at it from the natural perspective, from the geochemical perspective. But remember, natural water resource management is a very interdisciplinary, integrated science. So they used very high resolution images to look at, and what they found was that presence of certain type of chemical compounds like oxidized sediments to protect the deep groundwater from arsenic contamination. Why? Because these chemicals, these minerals actually hold on or absorb arsenic to its surface. What they also noticed is another mineral, pyrite. Pyrite is a sulfite mineral. So sulfur and arsenic seems to go hand in hand. Pyrite forms after the sediments have been deposited and during the process of its burial. So when you're adding pyrite to the system, what is important to know is how much of arsenic is it's sequestering in the mineral deposits. So that is something that needs to be studied better, but it's very important to understand this. It's a geochemical defense for protecting groundwater body from contaminants. So looking into these materials is very important. So if you look at the image here, don't worry about the details, but what is important to look at here is I said that they measured arsenic concentration from a number of wells. So those in the green here that you see, most of them, the arsenic concentration is actually in the very acceptable level. So that keeps this area safe from the drinking water perspective. But the recommendation by this research group from UCL is very, very important. They said that so long they're using deep hand pumped wells, these regions are going to remain safe. But when they start using widespread deep irrigation pumping facilities, the deep groundwater protection will be eliminated and arsenic will be percolating down. So this is a future forecast that they want people to be careful about. And why is that? Because there is something called a flow pattern defense. When we are talking about the aquifer, we need to take into account about the aquifer geometry, the rock types in the aquifer, and those are the things. And obviously the hydraulic conditions that's going to govern the water flow. Those things are very important. Those things are something students of water management should be acquainted with. What you're doing when you start using the deep hand pumped wells, you are making opportunities for vertical flow of water in between the layers, because the layers of rocks, you can imagine these rocks to be different materials. They give us kind of anisotropy, heterogeneity to the whole system. So the moment you make this deep hand-pumped wells, you allow the vertical flow of water and let the contaminants reach the deep groundwater storage and affect the fresh water that people would be using. These are images that are very global in context. So what you look at is an eutrophic lake, and what you look at this one is acidic water from a mine in California. So we have been talking a little bit in the previous few slides. We've been looking about groundwater contamination in the subsurface level. When it comes to the surface level, it is equally important to manage the water properly. We don't want to have a eutrophic lake like that with excessive algal growth that affects the water quality. And the reason for this kind of excess algal growth is because it has too much of nitrogen, it has too much of phosphorus, it has too much of nutrients that promotes the growth of this algae. And we do not want this acidic water because it's contaminated with different elements that are harmful for us, besides not just arsenic. So we've been talking about arsenic in the previous slides. So then what comes into question, and then what is important, is how do we solve this? So those are wastewater, the wastewater that made their way to our water bodies, the water bodies that we rely on for the supply. So how do we solve this problem? How do we treat this problem? One is the nature-based solutions that is based on natural processes. So what we can look at in this perspective, use a natural setting or create a natural setting that mimics some natural processes. And this can be applied in many scales, at a micro to the macro scale. There are very important studies, groundbreaking studies going on in UCL in the chemical engineering department, led by Professor Mark Olivier. So what they looked at is if you look at the different organs of a human body, like the kidneys, they work in ways to purify the liquid. So they are trying to use that natural understanding in an artificial setting. For example, if you look at these natural membranes, they have different pores, aquaporins, that repels ions but allow water to be transmitted through. They're studying the nature of the spores and try to take that learning to build artificial membranes. So those are the kind of important research that's going on in the Department of Chemical Engineering and UCL to address, to find out some solutions for better water management. And this one particularly specifically related to wastewater treatment. Here is another example where nature-based solutions can be used for wastewater treatment. So that is constructing some wetlands. When you construct the wetlands, you use plants which can be a mix of submerged, emergent, and floating vegetation. And you can have this kind of constructed wetlands on the surface, or you can create them in the subsurface. So there are two ways of doing it. And how you percolate the water, you can initiate a horizontal flow, or you can initiate a vertical flow. So what is done is passing this water through different filters, then they undergo the process of, they are treated before they finally collect in a drain. So this is very important to note. A lot of its planning goes into it. So that's going to actually dictate the performance of this constructed wetlands, and it's a subject of very detailed study. So whether you have vertical or horizontal, and then how you have the different layers of rocks and materials, and how the rate at which you percolate down the wastewater, and then how you treat them before they are drained into in a place where they can be stored. So there is an advantage, obviously, because it's mimicking a natural situation. There's a large surface area where wetlands can be created, and it can help in the physical chemical retention and biological reduction of organic matter and nutrients. That's a big, big advantage. But there is challenge because temperature affects the performance. It works very well in cold countries, but not in all places of the world. As I said before, it depends on the design. It depends on the loading, hydraulic loading, and the retention time as the water infiltrates through the different layers. And it cannot meet the standards we expect for heavy metals and nitrogen. So that's where research comes into play. How do we improve this? So when you think about the wastewater treatment from the nature-based solutions, if we move into a treatment plant, there are some preliminary treatment methods before we move into secondary and tertiary treatment methods. So preliminary treatment methods is like the grit removal, it's like the screening. In some plants, they use a rotor so that you get rid of this big particles that can block your pipelines later on. You have the solid removal that uses a media. It could be like a cloth media, then filtration to the membranes, and then the dissolved air flotation treatment. So there are different treatment methods to remove the impurities, contaminants that are present. And finally, you have the nutrient removal as well. The nitrogen and the phosphorus being very important because until you manage to remove them efficiently, and they make a huge content of the pollutants in the wastewater. And unless and until they're treated properly, they will end up in the water bodies. And you've seen a few slides back what can happen in terms of eutrophication. The processes behind these technologies are again simple, like adsorption, disinfection, flocculation, nutrient removal, and oxidation. When it goes into degrading the organic matter, that could be chemical oxidation, and it could be biological oxidation processes as well. So this is a workflow diagram of a wastewater treatment plant. This is what chemical engineers work with a lot of time. So you can have the primary settling tank where you put in the raw wastewater firstly, you filter it, pump it, and put it in a settling tank where you rely on processes like sedimentation. It undergoes biochemical treatment, and again, you put it through another settling tank. There is disinfection using different kinds there are a number of methods. So this is a very detailed area of studies, different disinfecting methods, and then discharge or tertiary treatment. What is also important to note here is this is the wastewater treatment, and then you generate a lot of sludge from this whole process. The sludge again needs to be treated. The sludge needs to be thickened so that it can be worked on. Then the sludge digestion before you dehydrate the sludge by dewatering, and then filter cake outboard transport. And the important thing is, what do you do with the sludge after that? So these are very important consideration, and there are a lot of research going on in each step of this. So this is what the sludge is, the product that you generate after the wastewater treatment. The sludge is something that you do not always want to end up in a landfill. Obviously, even before ending up in a landfill, it has to go through some processes that we just discussed in the previous slide, like thickening, stabilize the sludge, and dewater. But it's important to consider whether the sludge can be used to recover different products. For example, that can be used for composting, building materials, energy regeneration, etc. An important area of research in in chemical engineering and interdisciplinary science. So there are, as I told you, when you're talking about the wastewater treatment of the sludge treatment, there are some details going on. I just want to give you an idea how it has developed right from the start. So this is an activated sludge process. I'm talking about many years back, 1912, 1914. As you can see, that it was very simple. It has an aeration tank. It had a final settling tank, and then the waste activated sludge, if you notice, it goes back again to the aeration tank. It was as simple as that. So aeration tank, where it removed the organic contaminant by oxidation. Settling tank, where the process of sedimentation was used so that the purified water could be separated from the sludge, and then the sludge again went back to the aeration tank. So this was a process that was used way back, and the processes have been improvised consistently. And this is just to give you an idea what goes on. I'm not going to go into the details, but to tell you that this is a very common process that is now used for nitrogen removal. So anaerobic, anoxic, oxic. And then again, the sedimentation tank, and then the return sludge. So you see, it has retained elements from the design that was previously used, but it has undergone a lot of modification. The basic idea is when you have nitrogen, a lot of it is going to be in the form of ammonium. It needs to be oxidized to nitrite, then it has to be oxidized to nitrate. Finally, it is converted to nitrogen. So that's like a simplified process on how nitrogen is removed from the wastewater. But what is important to note is, because you need a lot of oxygen when you convert the ammonium to nitrite or the nitrite to nitrate, there is a huge requirement of energy. That is something that people are trying to cut down. There was a student working on a dissertation project to look into alternative treatments like Anammox bacteria instead of going through the cyclic process of ammonium to nitrite to nitrate. So there's a lot of interesting research that can go on to address these issues. When it goes to phosphorus removal, I just want to give you just one idea of the kind of research that's taking place, because phosphorus has to be removed in a solid form. And we are, as I said, we're trying to look at everything from the perspective of a circular economy. Can we recover the phosphorus from the sludge? How can we get it back? Because phosphorus, as you know, it can be a very useful ingredient. But what was not understood well previously is the understanding of the solids that are forming with the phosphorus. So what researchers have been able to find out using very high detailed images is like they form compounds like vivianite. This is an iron phosphorus compound. Why iron? Because iron used for dosing for phosphorus removal. What is the challenge now? The challenge is that vivianite is very, very small. So that's still a challenge that needs to be addressed, but at least we understand better about the compounds that are forming in this purification process. So we are making, the technology is advancing in order to make this water management a bit more efficient. Because if we can recover the phosphorus, that is going to be a breakthrough. And for that, we need to understand the compounds that are forming in the process, the solids that are forming in the process of phosphorus removal. So as I said earlier, these are the technical developments. Everything, the water demand has to be considered from the perspective of climate change, how the spatial and temporal patterns and precipitation is going to change in the decades to come, how the temperature increase will affect of the hydrological cycle, because the very assumption that the hydrological cycle is stable is incorrect, and it's going to affect our forecasting for the future. Then about the dissolved oxygen that is present in the water. So because the dissolved oxygen amount is very critical in terms of the pollutant retention. So everything, there are so many aspects that needs to be considered in the water management by scientists to improve our water usage pattern. And if we have to meet the UN Sustainable Development Goal by 2030. So with that, I would like to end my talk now, and I'm happy to take any questions. I tried to give you a flavor of what we do in the module connecting with various research areas. And this is, as I said, as you might have understood from the talk, it's a very, very broad subject area, but it's very interesting and very much the need of the hour for future. So with this, I'm going to stop sharing my slide. Okay, I can stop my sharing. And if there are any questions, I'll look at the Q&A panel. And I'm going to answer your question. Okay, I think very interesting questions there. The first question from you is, you've shown that there are 5 main valuations of water. Is there a scale of priority for them? If we were really forced to choose, which one do you think would be the safest to dispense with? That is a very, very interesting question, very critical question. And the reason the valuation of water is so very difficult to do, because we consider the different domains in terms of the storage, in terms of in situ availability, in terms of the need of the water for different sectors. And we also took into account the spiritual and the cultural perspective. We cannot number one above the other. It's going to be very dependent on the different nations we are talking about, the perspective, because a country might be much more advanced in, say, water treatment, whereas it might be behind in terms of in situ water and the availability of in situ resources, whereas the reverse can be true for another country. So the water valuation in numbering these domains is very difficult. It's not going to be possible, but it needs to be taken on a case-by-case basis. So if you're looking into a particular scenario, you have to delve in details in all these domains, all the 5 domains, and then you can think which one can be prioritized in lieu of the other. For example, if you see a country that is very focused on agriculture, you would naturally like to, and you have to measure how much water resources is available, in situ water resources. So depending on that, you can make an assessment whether you should focus on water usage pattern, or do you focus on water treatment. So that's how you can make a fair assessment, by looking at it very specifically. I hope that answers your question. Okay, in the characterization of wastewater, what does BOD, BOD5, and COD mean? So it's biochemical oxygen demand, and then biochemical oxygen demand, BOD5, is biochemical oxygen demand measured over a 5-day period, and COD is the chemical oxidation demand. What it actually does is it gives you an idea about the pollutants that's present in the wastewater, because if you measure the dissolved oxygen in, say, day 1, and if you measure the dissolved oxygen in day 5, you exactly know how much oxygen has been consumed by the bacteria in trying to degrade that organic matter. And by the chemical oxidation demand process, the oxygen will also be used for the oxidation of some reducing species like the chlorides and other inorganics that are present. So basically, taken together, they'll give you an idea about the pollutants that are present in the wastewater. This is a simplistic answer. There is a lot of details in it, but Broadly, they give you an idea about how the oxygen how much oxygen is being consumed either by the bacteria or by the different chemical processes integrating the pollutants or the organic matter. Okay. The other question is, you have stated that one of the inadequacies of wetland is that they don't really deal with heavy metals. Bioremediation, especially phytoremediation, on the other hand, has been known to be able to be dealing with heavy metals. What's your opinion on phytoremediation? Would you say that it is potential to be used on a live scale? On a large scale, okay. So this would actually, I think there is a lot of potential, but I cannot answer on the scale of studies that's going on. So it would need a little bit more research on my part to give you the correct answer. But I do agree that it has a lot of potential, but I won't be able to specify the scale at this stage. But as you have pointed out, you're trying to say, yeah, bioremediation as on the whole might be an alternative. If you're trying to say it's an alternative to constructed wetlands, I wouldn't say it's an alternative. It can go hand in hand, I would say. But I think one thing to be noted is constructive wetlands work in cold climate. It doesn't work well in the warmer climate because it can be very temperature sensitive. It also depends on the organic loading, where bioremediation can be a better alternative. So again, I would say that we need to be very careful as to where we are talking about in terms of the application. And regarding the phytoremediation and its scale, I think there needs to be more studies, and I need to look at it in terms of the scale a little bit better to answer that part of your question. But thank you, that was a very interesting, important question. There are some types of wastewater that are very difficult to deal with. Wastewater from printing industry, what more sustainable processes would you recommend to deal with this kind of wastewater that uses less harmful chemicals? So when you are talking about sustainable processes, would you recommend to deal with this kind of wastewater that uses less harmful chemicals? What immediately comes on the top of my mind is focus on regeneration and recovery, therefore treatment. And this could be done on a smaller scale. Like if you're talking about one printing industry, and yes, you're talking about one printing industry. It's not exactly like gray water recycling. When we talk about the gray water recycling, we are talking about it in UCL building scale, looking at the water from the showers, from the sink or from the washing. So where the purification is not so it's not so intense. So you use less energy, you use less of the other resources. I would say that is where one should focus on, to look at more local or a smaller scale purification or treatment facilities within the particular industry. The next question is, in your last slide, you said that dissolved oxygen affects pollutant content. In what way? Yes, dissolved oxygen affects pollutant content because oxygen has a way, we all know, depending on the conditions, obviously, whether you're talking about an oxygen setting or an oxic setting, oxygen can be very reactive. It can combine with various pollutants. And once it combines with pollutants, there's a way of segregating that pollutant from the water. It might settle down, it might devolatilize. So all kind of following the chemical reactions, all kind of processes can occur. And also the degradation time, you should be very, very much mindful of the degradation time of the pollutants. So it is very different from one form to other. So after a chemical reaction with an oxygen, that's going to change. And that is why the pollutant content changes. The next question is this module available for the undergraduate program? This module has been, at the moment, designed for the postgraduate taught program, but on the other hand, if undergraduate students show a lot of interest, it's definitely up for discussion. So this is something I can take this question back to my department. So do be in touch for an answer. And in which year do we cover this module? This is, at the moment, a postgraduate taught module, but related to the question prior to that, is this module available for the undergraduate program? If there is a lot of interest, it is something I'm sure the department will consider, and we can take this, I could take this question to the department. So yeah, thank you for joining us today. And thank you for being interactive, for asking your questions. If there is nothing else to answer, I'll just have the chat, okay? Yeah, so there is nothing else for me. And if there is nothing else from you, we can end this now. Thank you, everyone.